The first slide is an introduction to category theory. I was saying that in category theory, most of the times we study large mathematical structures where objects themselves can be smaller mathematical structures. And one can think of this as a sort of cosmology of mathematics. On the picture, we see gray blobs. These are, in a sense, stars. If you like to think of them as stars, each of the gray blobs is a universe of its own. They're called categories, and then there are various interactions between these categories. Now, to describe the interactions, first we need to understand what happens inside a category. Well, inside a category, there is a similar picture. There are smaller blobs, these are the dots, and they interact with each other in various ways. These interactions are called morphisms. We can compose morphisms, and basically category is the algebra of composition. It's associative, has identities. The sample category there, the category of topological space, you see a circle, and a circle on a donut by going around its middle hole and also the hole inside the donut. So the donut is hollow, inside there is nothing. And then you can associate to each of these topological spaces a group, the fundamental group, which maps you from the category of spaces to the category of groups, which is on the right-hand side. For the circle, it's the group of integers. Basically, this group is all the ways you can go from a fixed point to itself. You can loop around a few times around the hole, which you cannot squash because there is a hole in the space. So you end up getting what is called non-homotopic paths from the red point to itself. And because of the direction also, then eventually we get integers where positive means one direction and negative means the opposite direction. For the donut, for the torus, it's the integers times the integers. And then the continuous maps you can have between spaces would give rise here to group homomorphisms. And this process preserves composition as well. Remember, a category is the algebra of composition. So obviously, when I relate one category with the other, I want to preserve that. All right, so this picture is just for fun, although the thing displayed here, the functor from the category of topological spaces to the category of groups, the fundamental group functor, is a very important construction in mathematics, and there are many other such important constructions from one universe of mathematical structures to another. There is also a second slide which gives a bit more insight into what we do in categories. In fact, small-scale structures also form categories often. For example, every partially ordered set can be regarded as a category. You see there a picture in area 2. It's the picture of the partially ordered set of subsets of a 3-element set. And the arrows there describe subset inclusions. We only draw on this picture the arrows that we need to generate all the others by compositions. So you can think of this as one subset being less than the other when there is an arrow from one to the other. Then there is also a case where we have one object and all arrows are reversible. These are exactly groups. Categories with one object with all arrows reversible are exactly groups. And you see the picture of groups of the group of integers modulo 2 in area 3. In area 4, we have another category where objects are sets. Interestingly, if you take the disjoint union of sets and Cartesian product of sets, you'll get mappings that relate these sets with the original ones. For example, from x to x plus 1, x plus y, the disjoint union of x and y, you got the inclusion map. Map everything in x to its copy in the disjoint union. And same you have from y to x plus y. And then there is a nice universal property that this diagram of x, y, and x plus y obey, which is that for any other set C and maps is drawn there, you'll have a unique connecting middle map, making the triangles commutative, which means that the composite of the map from x to x plus y with x plus y to C gives you a map from x to C. And for Cartesian product, is also for the other triangle, the same condition. For Cartesian product, we have also a kind of universal property. This time the maps go the other way around. From x cross y to x and y, you have projection maps. And one of the things that category theory shows us, which we never knew when we were studying arithmetic, is that addition of numbers and multiplication of numbers, when they are presented as operations on sets, can be regarded as dual constructions. As you see, the conditions are the same, just the arrows reverse. And that's the idea of duality in category theory, when we take a statement or a theorem and reverse the direction of all the arrows there. Okay, so the first two lectures assumes that, the first two slides, sorry, assumes that I've managed to equip you with a good mastery of category theory. So now we can go to a specialized talk about the subject. If you have any questions so far, if anything is unclear about this subject, please feel free to ask before we proceed with a slightly more technical talk.
You don't want to make it full screen, I think, until you want to write it.
Thanks for that suggestion. The thing is that I have a continuous slide, so if I make it full screen, it will show the whole thing. Yeah. And I don't know how to remove the menu. Okay. But I think everything what I wanted to fits there. So, okay. All right. So let's move on. In this slide, I'm going to explain what is a form. Now, the word form is definitely used many times in mathematics. This specific use so far only appears in either papers of mine or my collaborators on this topic. There are many ways of thinking about them. I would like to think about them here as functors. So basically, a form is a functor from B to C. B is a category, C is a category. So each of them are universes of objects and arrows between them, and the functor F connects these categories. Now, there is a certain intuition about this. First of all, we want to think of this as a structure that C is equipped with. So C is the main category we're working with, and we want to study the category C by putting this F over it to understand what's going on in the category. It's very similar to the idea in topology, where you put a bundle over a space that you want to study your space. And this idea goes back to Grothendieck, who actually transferred the concept of fibration from topology to category theory. Our forms are indeed going to be bifibrations in the sense of Alexander Grothendieck. So there will be fibrations as well as obfibrations. But they will also satisfy an additional condition which makes things a bit easier, and that is faithfulness of the functor and also being amnestic. Being amnestic means that the fibers are going to be not just arbitrary categories, but they're going to be posets. There is an equivalent way of describing the structure of a form when for each object X we specify this poset of so-called clusters in X. And then for any two objects B and A that map to X and Y, respectively, as you see on the picture in area 2, we will write that B is bigger or equal to A according to F when the morphism F lifts in the top category to a morphism F bar from A to B that by the functor F maps down to small f. And the condition of lifting is written in area 4. And then in area 5, we reformulate what it means to have a form. Basically, it means that we have a family of posets, one for each x. The f minus 1 x is the poset here. And then we also have relations between elements of these posets, which satisfies the index transitivity law that you see in the middle there, and the reflexivity law as well. So this is equivalent way of describing a functor. In fact, there is a sort of Grothendieck construction type of process here that links the two ways of thinking about it. Examples are many. These are just faithful amnestic functors that have been studied in the literature for many years. Sometimes they're called concrete categories. Topological functors that have been studied a lot in South Africa are also forms. In the case of a topological functor, your fibers are complete lattices. So you take the category of topological spaces and you assign to every topological space a set. You get a functor. But usually when you do that, your main object of study is topological spaces. Now I want to think of sets as being the category I want to study, and I will be studying every set by looking at all topologies the set can come equipped with. So that's what I will be doing if I want to think of this thing as a form. Any monadic functor is also faithful and monastic, hence it's a form. In this case, on the example 2 there, from vector spaces to sets, you'll take a set and you'll ask yourself, okay, can I understand the set better by looking at all the vector space structures on this set? And of course, in these two cases, it's a bit silly to try to understand sets by looking at topologies or vector spaces over it. So for our purposes, topological functors and monadic functors are not going to be the most interesting, at least these kinds of topological functors are not going to be the most interesting examples of forms. But the third one is the one that we would be interested in indeed. If you take the category of groups, there on the left side, this is algebraic topology notation, pairs of groups, the category of groups and subgroups. So that means that for every group G, you'll be looking at the poset of subgroups of this group. And now we want to study a group and group homomorphisms between groups by examining how they interact with the subgroups of the group. And this turns out to be a useful tool. And I will show you why now.
Okay. Can you just do it again then? So let me a bunch of concepts I didn't understand. So F inverse of X, the category of clusters in X, what do you mean by that?
That's the fiber of the functor. So that's all the objects upstairs.
You just want to give it an interpretation.
No, I will use the term cluster as a general term for something living inside the fiber. But
it doesn't have a technical definition.
That's the definition. No, it's just
it's an object in the fiber.
That's right. Yeah.
By the fiber, do you mean like the fiber as a category or just a set? What is it?
As a category. The morphisms there are those that map down to the identity morphism. Yeah. Okay. That's an important question. Yeah. Yeah.
Okay. And then I didn't quite understand the definition of being a form. So F has to be faithful. Fine.
Yes.
Amnestic.
Amnestic says that if you have an isomorphism in the fiber that maps down to identity morphism, that isomorphism must be also identity, which amounts to saying, you see, faithfulness guarantees that the fibers are preorders.
Sorry, are preorders.
Yeah. And this condition, amnesticity, amounts to saying that these preorders are actually partially ordered sets. So antisymmetry holds. If X is less than Y and Y is less than X, then they must be equal.
Well, what's a little bit confusing is your drawing. Like in your drawing, it makes it seem as if A and B are in the same fiber, are in the fiber of X.
Well, B has an arrow mapping down to Y, right? So we want to interpret this as B being in the fiber of Y.
What's confusing is that so B thought it was being in the fiber of Y, fine. But then you also seem to be saying that F inverse of X is a poset. So, and then you're saying that B is in that poset. So that means that it's in the fiber of X. So that's the thing that's confusing me.
Am I saying that B is there? Where am I saying that?
No, like you're saying that B is greater than or equal to A. It's as if you're defining the partial order on the fiber.
So the partial order is defined between the fibers. So that's
you mean the entire B is a poset? The entire category?
No.
Yeah.
So we take elements in one fiber and elements in the other fiber, and we compare them with each other based off a given morphism downstairs. That's why there is an index F there. So it's a generalization of order relation, which is, we can think of it as indexed ordering, where the indices are morphisms in the category below.
Okay, so I forgot again what the definition of amnestic was.
Forget about the definition of amnestic. Just think of it as the fibers being posets. So inside the fiber.
The weird thing is that you're saying there's two things going on. You're saying the fiber itself is a poset.
Yes.
And you can compare things in different fibers. There's two things going on.
That's right. And the thing that's going on inside can be recovered from the thing that's going on outside by the first inequality there. A bigger or equal to A means A bigger or equal to A according to the identity morphism. So the poset structure inside the fiber is the indexed poset for the identity morphism, where the index is the identity morphism.
Okay, I'm a little bit clearer. But
Yeah. So transitivity for indices, if you take G and F there for the transitivity rule to be identity morphisms, then you get usual transitivity inside the that stays inside the fiber.
Maybe a few more pictures and I would be better. I would be in a better situation. But
all right.
Maybe they will come.
Is a form any faithful amnestic functor or a
Yes.
faithful amnestic pi vibration?
No, it's any faithful amnestic functor. But yes.
Zurab, do you really need it to be a poset for any sense or for any reason, or just taking a pre-order would suffice?
For the same reason as the world is using posets. So everything you do on posets can be done with preorders up to isomorphisms of elements. The same applies to forms. It's just more convenient to write equality instead of isomorphism between elements.
And you don't have to bother about the naturality of the isomorphisms, I believe.
No, everything is fine.
Yeah. Okay, thank you.
Look, the notation is new, right? This notation, the indexed inequality notation, appears first in my paper with Marino Gran and Mathieu Duquert-Antoine. But it's not completely new. You can see some of it in appendix to one of the books by Lovier on logic, where you have turnstile with an index. And that turnstile with an index is an example of this, actually.
So what you're saying is that every time I've got a faithful functor from B to C, I can always interpret the elements of B as there being a
preorder. Yeah. If it's only faithful.
It's as there being a preorder on just on the objects of B, or sorry,
an index preorder.
An index preorder. I have to think it through.
Yeah, I also find this a bit confusing because it's only equivalent to being.
No, this is wonderful that it's confusing because it means that I'm saying something interesting and new.
It's only equivalent to it being a poset, right? If it is some kind of vibration, right? Or like a
no.
index poset.
Faithfulness gives preorder, right? We don't need a vibration property yet. Faithfulness gives a preorder. Why?
A preorder or a collection of preorders indexed by the.
A preorder on each fiber.
Preorder on each fiber.
Sure.
I can't think. Maybe you do get a. I think you do. You're right. You get a preorder on each fiber, but you can't. Can you compare the fibers in general?
Yes, whether by whether the F downstairs lifts or not. If it lifts, because the functor is faithful, if it lifts uniquely.
Okay.
So if it lifts, hooray! Then we write B is bigger or equal to A according to F along F. If it doesn't lift, we don't write that.
Okay, I guess the point is then that maybe doesn't contain all the information of the functor.
Full information about the functor. Everything you need to know about the functor is there.
I find this a little confusing, but okay.
Okay, but it's interesting that this is something that's not immediately clear. I mean, I always assumed it would be clear. You get full information about the functor. In fact, a lot of times, I mean, this is the growth and deconstruction story, right?
No, but that's what's confusing me. If it were the growth and deconstruction story, it'd have to be
it's a more general version of the growth and deconstruction.
Yeah,
we're not going here in the category of posets and monotone maps. No, we're going into the category of posets and so-called connections, which is something a bit general than Galois connection. It's a relation that's actually a profunctor between posets.
Okay. Yeah. Yes. So it'll be yes. So that I understand. If you have a general faithful functor, it'll correspond to a lax functor into the category of relations, right?
If you have what, sorry?
Like a general faithful functor is equivalent to a lax functor into the category of relations.
Yeah.
And then so each fiber would be a monad in the category of relations, which is a poset. But I guess it's just.
Yeah, the monad story I don't know, but yeah.
So if you have two fibers and A is in one and B is in the other, and A is bigger than B, is it the case that all other objects in the same fiber as A are bigger than all those in the same fiber as B? So can you order the fibers, or is it just the elements in the fibers?
It's the elements in the fibers that we're ordering. Look, it's very clear what's written there. So we write B is bigger or equal to A according to F when B maps down to Y by the functor, A maps down to X by the functor, and the morphism F from X to Y lifts in the top category. So there is a morphism F bar from A to B such that the functor applied to F bar gives me F. Because the functor is faithful, there is a unique solution to this equation always. There is always unique F bar. And because there is always unique when it exists, we can think of this as a relation between B and A.
Yes, you're very right. And if you take any other A prime in the same fiber as F inverse X and B prime in F inverse Y, if B is greater than A by F, then B prime is also greater than F by A prime. That's also true. So it's actually it's actually comparing the fibers also. So the full sets are being compared.
I'm not sure I follow that, Partha. I think we need just a bit more.
If you take A and A prime in the same fiber, B and B prime in the same fiber, and if B is bigger than A, then B prime is also bigger than A prime.
The A and the A prime also should be related to each other, and also the same for B and B prime in order for what you say to be true.
Yeah. Yeah. So in some sense, you are actually comparing the full cluster by writing B greater than A by F. The full cluster of X is in some sense bigger, smaller than the full cluster of B, of Y.
So let's do an example, right? If this is challenging, let's do an example. To do an example, I'm going to actually I think I can write here, right? So okay, so what can I erase here? I think I can safely erase this part, or at least move it, or at least make it smaller. There we go. And let me use, okay, so the red. Can we see this? Okay, it's going to be a tiny example, but there we go. Oh, that's a good idea. Thanks. The question is, well, I'll be able to find it quicker than the answer is no, so I'll continue doing it manually. I think this is big enough, yeah? So let's take the example that's going to be relevant to us. Groups downstairs, the category of groups, and upstairs we have pairs of groups, a group G and a subgroup H. H is a subgroup of G. The functor maps this pair to G. Actually, in my mind, I don't want to think upstairs to be pairs. I just want there to be subgroups there. The only problem is that subgroup doesn't remember of which group it is a subgroup. You can have the same subgroup of many different groups. So that's why we need to keep track of the group from which we took the subgroup. So we get pairs.
What are arrows upstairs?
A group homomorphism that map subgroup into the subgroup in the other one. So if I have groups G and G prime, and I have a group homomorphism, F, and if I have H, a subgroup of G, and H prime, a subgroup of G prime, then I can ask whether in my notation H prime is bigger or equal to H along F. The answer to that question is whenever F of H is a subgroup of H prime. F of H is contained in H prime. According to how I define the morphism, that's exactly the same as to say that there is a morphism upstairs, the same F, but now seen as a morphism between pairs that maps down to this F.
Right. fine, but that at that stage it's just notation. But the question is whether you can think of this dually. So the question is whether such a structure is the same thing as a functor from the base category into sets or something, you know, like into posets. You expect you lose a little bit of information there?
You don't lose a little bit of information, and I'm very happy to give another talk about that. Okay. It's actually also explained in the first section of the paper I'm going to share at the end of the talk if I reach there. There we go. But yeah, so for now, just trust me that everything is fine. We actually capture the full information about the functor. And if you don't want to trust me on that, then just think of it in this notation way, not in terms of the functor. So the whole point is to put conditions on the functor that we haven't considered before. The reason why I wanted a new term for a faithful amnestic functor is because I want to put adjectives in front of it. And if I keep faithful amnestic functor with the adjectives, it becomes too long. So I call it the form. By the way, there is an example in logic where things in the fiber are formulas. So that the name form kind of corresponds to that. Another reason for the term form is that, as it will turn out, you can begin with a category and you don't know if it has a nice form or not, but you can find one. And in my mind, when you find one, I think of it as having given a different form to the category. So something has been revealed that wasn't clear from the beginning.
Just that I understand correctly, so in other words, I really can't think of a form on C as a function from C to posits.
When it's an Orion form, you can start thinking of it like that. Orion. Or was an algebraist in the school of Noetherian who introduced, formalized the notion of Galois connection. Birkhoff did it, I think, at the same time, so it's not clear exactly who did it first, but he wrote a couple of papers, I think in Annals of Mathematics, if I'm not mistaken, where he develops abstract algebra in the language of substructures of algebraic structures. And what I'm telling you today is categorical extension of those ideas. So these are the axioms on the form. Let's go through them. The first one says that these fibers are bounded lattices. You have joins, you have meets, you have top, you have bottom. And always when you read these axioms, think about groups and subgroups. So F-1, think of that as the poset of subgroups of a group X, okay? Then you agree with me it's a bounded lattice, right? The bottom element is the trivial group, the top is the entire group. A meet of two subgroups is just their intersection. Join is take their union and generate the smallest subgroup. If one of them is normal, for example, it will be the same as just multiplying them. Okay, so the second axiom says that you can do direct images and inverse images. This is direct image of a subgroup along a homomorphism F, and this is the inverse image.
Why do you use that notation? Just you like it?
For two reasons.
Okay.
One is that because I like it, and I thought I invented it, but then I also found the same notation in Lovier's same appendix that I told you about, where he uses, for substitution, he uses this notation. So I was very happy about that because I knew that people would question the notation. The convenience, of course, in this calculus is that you see the equivalency. You take F, you drop it down as an index, or you take it from an index and you put it up on the right side. So the notation kind of suggests what the rules are. The fact that this equivalence holds, we all know quite well, at least those of us who are familiar with Galois connections, is an inverse image and direct image, a junction between posets of subgroups. This is functoriality of the direct image and also of the inverse image, which is also quite evident for groups. Take a subgroup A, take its direct image under F, then under G is the same as taking direct image of A under the composite GF. And the same rule applies for inverse image. Okay, now the main axiom, okay, we're not to the main axiom yet. So the next one, so we now covered 3 axioms, and if a form satisfies these 3 axioms is 1, 2, 3 in red, then we call it an Orion form. There are 3 additional axioms in order for it to qualify being a Noetherian form. The 4th axiom is a factorization axiom. It will ensure that you have a nice factorization system in your ground category. So how you factorize a morphism F? You take its kernel. Well, the kernel can be defined as the inverse image of the bottom subgroup. You take its direct image, which can be defined as the direct image of the top subgroup. And notice already that inverse image and direct image become dual constructions because direct inverse image are dual and top and bottom are dual. And then you turn them into morphisms. How do you turn a kernel into a morphism? So it's displayed in area 3 here. So imagine I've got a kernel of F, okay? I want a morphism pi that kills the kernel. That means that it maps the kernel into the bottom subobject here by direct image. But I might as well just drop that condition. I just want a morphism pi, and instead of that, say that I want a morphism pi such that the kernel of that pi is bigger than the kernel of the original thing. And then if I have another p whose kernel is also bigger than that thing, then there must be a unique morphism U. It's just a universal property of quotient of a group by a normal subgroup. This is the dual situation, which allows me to view a subgroup as a group of its own. So if Y is a group, sorry, is a subgroup, sorry, Y is a group, right? But now the image of F is a subgroup, and this thing will be that subgroup viewed as a group. I can lift, when I have something upstairs, let's go back to my previous picture. When I have G and H upstairs, there are 2 ways I can bring them down to the bottom category. One, by quotienting out by H, when H is normal. The other, by considering H as a group of its own. And this map is going to be called iota H, and the other one is going to be called pi H. So this is what I'm trying to explain here. By the way, if a form was such that it allowed these constructions for every object B, then we would end up with a nice simplicial picture. The functor has inverses given by bottom and top element in the fiber, and there will be 2 further adjoints there, giving rise to these constructions I described here, but I'm not going to go into that right now. And then we require that when we do this, it is possible to then factorize F as the pi of the kernel composed with a iota of the image. In groups, all this says that if I have a group homomorphism from X to Y, I can decompose it as a surjective homomorphism followed by an injective one. It's basically the first isomorphism theorem for groups. Okay, this condition is more interesting. Yes?
Yeah, but so you want some kind of exactness on the inverse image and image constructions. That's what you're saying in the next line. Cur F1 and join cur F2 is cur F3.
Yeah. Yeah.
Oh, thank you.
Let me first give you an insight in this second equality. For that, I'm going to make another white space for me here, if I can. Control X. There we go. Imagine you have 2 sets. They don't have to be groups. Just 2 sets, X and Y. And imagine you have a function that maps X into Y, function F. If I take a subset of Y, call it B, and I take its inverse image and then direct image, I will get this piece, right? But that's exactly the intersection of B with the image of F. So we just proved that this formula holds for sets, therefore also for groups, because direct and inverse image for groups behave the same way as for sets. The second formula does not hold for sets. Okay? If you've heard of lattice isomorphism theorem for groups, that's what the second formula establishes. If you go to the algebra textbook by MacLean and Birkhoff, they first prove the lattice isomorphism theorem, and then they derive the isomorphism theorems of others from this one. This is the first encounter of protomodularity. Because for a regular category, we take the form of subobjects. This formula, the joint formula, will be equivalent to protomodularity. And the fact that we can use that to conclude other isomorphism theorems is something that MacLean and Birkhoff already noticed, but they didn't have a language to formalize it abstractly. They just use it as a tool. And what we do in a Noetherian form is basically to say that, okay, actually, what they do in that book, we can actually use that as an axiomatic approach to this whole story. It's also a nice exercise for one to check oneself why this formula should be true for groups. I will not going to go into that right now. The last axiom simply says that if you take two normal subgroups, so two subgroups that are kernels of something, you join them, that is also a kernel of something. And opposite, if you take two things that are images of some homomorphisms, for groups, this is always the case, right? But for a general form, not everything needs to be an image. You meet them, you take their meet, then that result must also be an image of something. We call these things conormal when a cluster is image of morphism. Say that it's conormal. Okay, so now what I'm going to tell you is that these axioms enable you to recover not only all the but also the homological lemmas, the diagram lemmas in homological algebra. The snake lemma, the 3x3 lemma, the 5 lemma, all of these things. And many other variations of them. For instance, there's something called butterfly lemma, which is used to prove Jordan-Holder theorem. You can do butterfly lemma here as well. You can do Jordan-Holder theorem in the context of Noetherian form. Essentially, morphisms, that is true. So that's the power of it. Were we gone for a long time? Maybe.
Just whatever.
Okay. But I see that I should also be wrapping up, right? It's 5 minutes left. Okay, let me try to do this quickly. So if I have a zigzag of I want to determine whether that zigzag will give us to an induced homomorphism from Y, like in a snake, for example. And it turns out is that you just have to smaller subgroup of or small cluster in X. You chase it from left to right by taking alternation of direct and inverse images. You want to get the smallest subgroup here as well. And backwards, you take largest, you chase it back, you should get to largest. The thing is that if we did have a homomorphism running from X to Y, this would be true. Trivial subgroup under a homomorphism does map to trivial subgroup, and largest does map backwards to largest. But now we want to prove that this is really so in any Noetherian form. And how do we do that? The constructions for snake connecting homomorphisms of snake lemma in abelian categories makes use of properties of abelian categories, self-dual properties that are not true for, let's say, the category of non-abelian groups. So we can't use that construction. Snake lemma homomorphism in homological categories makes use of axioms that are not dualizable. So one had to come up with a completely new approach here, and the approach is what you see in the picture. You take each map, you factorize it according to the factorizations we have. The orange maps are, you take pullbacks of injections, for example, 2 injections. And I know it's a okay, let's do this again. So that condition turns out to guarantee that the green maps that are going wrong way, they're isomorphisms. And one can then also show that chasing things from left to right does not depend on the path. So chasing from X to Y is the same as chasing that way and then that way. And because of that, together with this condition I said, the wrongly directed green arrows will be isomorphisms and the wrongly directed orange arrows will be isomorphisms. So you can then compose all of this to get the morphism you're looking for. And you can really derive all the isomorphism theorems that I mentioned before, as well as the connecting homomorphism of something like snake lemma just by application of this. It gives a quick, by the way, it also gives proofs of these theorems that are quicker than for non-abelian groups, because for non-abelian groups, you always have to prove the two sides. Something is injective, then separately something is surjective. With this approach, we can only prove one and get the other for free because the context is self-dual. So we actually get proofs that are shorter than the ones for groups. So usually when we have categorical proofs, they're not necessarily short. I mean, it might be not more elegant from certain perspective, but they're not necessarily shorter than the classical proofs. Okay, now I have literally 1 minute to convince you that there are sufficiently many examples. But the thing is that the examples are so many that they're not going to fit in 1 minute. Let me just say that. Let me just skip to the next picture, where I'll tell you a little bit of story. So, there's something called Grandis exact categories, which lead one to distributive homological algebra, which generalize abelian categories, and something else called semi-abelian categories, which provide axioms similar to abelian categories, but those that work for non-abelian groups. However, this is not self-dual. So Noetherian forms bring these two things together. Moreover, by a result of Francois van Niekerk, we can show that actually even any algebraic category can be equipped with a Noetherian form. This is quite remarkable because we originally thought that these things are designed for group-like structures. But now it turns out that any algebraic category has these things. And one then asks, okay, what kind of isomorphism theorems do we get then? Well, in universal algebra, people have already worked out a long time ago isomorphism theorems involving congruences and subalgebras, and that's exactly what we get. The congruences will be the kernels, and the subalgebras will be the images of maps. But moreover, because any algebraic category is good, also the category of sets is good, and because sets is good, all toposes are good by embedding theorem for toposes. So actually, Noetherian forms also kind of bring together abelian categories and toposes, which is exciting because originally abelian categories and toposes were the most important categories studied in category theory in the beginning of.
Zurab?
Yes.
By algebraic categories, do you mean it in the sense of Adamic or in the sense of Lovier?
In the sense of Lovier, but I'm sure that one can also do it in the sense of Adamic. You mean many sorted?
Yeah, correct.
Yeah, I don't see any problem with many sorted, but I haven't thought about it, to be honest. Okay. Let me just say that while many results from abelian categories do generalize to Noetherian forms, this link is weaker. I mean, I'm not claiming that topos theory generalizes to Noetherian forms. I would expect that Noetherian forms capture very little bit of topos, not the full power of them. But still, the fact that every topos has a Noetherian form is exciting. Anyway, so this is now where I need to conclude. I actually didn't get to the main point of my talk, but that's fine. There are some open questions we have. I want to maybe highlight two of them. This one, does the category of topological spaces have a Noetherian form? Or maybe the category of locales or frames? Another question one can ask, does the category of sets and relations between sets have Noetherian form?
Surely the more precise question is, have a natural Noetherian form, or a Noetherian form that has the right properties.
Remember, being Noetherian already means that the axioms hold. So, no.
I just mean it might be possible to just put a trivial Noetherian form.
It's not possible to put trivial Noetherian forms. That's not possible. When you have a Noetherian form, you already can do something. At least you can do isomorphism theorem. So
you might say everything's isomorphic. You know what I mean?
There are Noetherian forms which destroy homological algebra, where we don't have exact sequences, but not really those that destroy isomorphism theorems, because some of them are actually part of the axiomatic. So it's not possible to put trivial Noetherian forms. It's possible to put trivial forms, but not Noetherian. So having any kind of Noetherian form is already a good news, and we don't know if we have that good news or not for the category of topological spaces. We also don't know whether we have it for sets and relations between them. We do know that we have for sets and partial functions between sets, because that category is isomorphic to the equivalent to the category of pointed sets, whose dual is semi-abelian. Therefore, there is no Noetherian form there. And just to one more thing I want to say. Sorry about this, but I'll finish in less than 1 minute. If you take the Noetherian form of the category of sets, right, and you take a 3-element set, and you look at what are its clusters. So for the usual form of subsets of sets, which is not Noetherian, you get a cube, or the power set of the set. For this one, you will actually get the lattice of partitions of a 4-element set. We turn 3 elements into 4-element set by attaching the base point. We turn it into a pointed set, and so we get this complicated thing on the left side, where you can interpret it like this. So, for example, this entity here is you partition your set, and then you choose one equivalence class. If choosing elements in a 3-element set corresponds to just picking a subset. Here, choice corresponds to almost like deciding how equally likely are things to be chosen and organizing them into equivalence classes according to that, and then eventually either finally deciding to make a choice or not. So you first organize things into equivalence classes, and then you decide, okay, do I want to pick this class or not? The posit is much more complex. Anyhow, so anyone who is interested to learn more about these things, there's a preprint with Francois, 68 pages, took 5 years to write it. And we're still writing it, I think. But we put the preprint up on archive in 2023. Thanks.
So I think that's a very nice idea, Zurab. Just one thing I want to understand a little bit better. For a Noetherian form, is there a way to describe it bottom up? That's what I'm looking for, right? So it's Noetherian form is a certain kind of function from D to C, right? The Noetherian form on C is a certain kind of function from D to C. It's a category D and a certain kind of function from D to C. Is there a way to describe that as a function from C outwards?
Yes.
What is that description?
So can I tell you that for Orion forms, which
for Noetherian?
Yeah, okay, that's the same for Noetherian. The description is that, so you've got your category C, and you go into the category of lattices with Gallo connections as morphisms,
Yeah.
adjunctions.
Simple as that.
As simple as that, yeah.
It's just a functor.
Yeah, it's just a functor from
So
here to there. That's all it is. Yeah.
Well, that's Orion, right? And then there's
Yeah. Yeah. This is for Orion.
Okay.
Bounded lattices. But no. But Noetherian form needs more axioms than
Yes,
this. But
I see.
yeah.
But which are those ones you stated? Can they be? Do they state a little bit more simply in the bottom up framework, or they're the same?
No.
You can't say it more simply.
No, you can't say it more simply. No. So the axioms that are trivialized by this approach are the first 3 on this picture, the one that are grouped under Orion. The last 3.
Well, what I can't understand is that like a 1-element set is surely a bounded lattice, right?
Yes.
Yeah, I think
So why can't you say a trivial functor?
You can.
What thing first?
So when C is a 1-object category, a Noetherian form over it amounts to having a bounded lattice over it.
Right? I'm saying like like an Orion form, you can always just use the trivial function, right? C just gets mapped to everything just gets mapped to the single element bounded lattice.
Oh, that will not be a Noetherian form. The factorization will,
But you can get an Orion form.
I think it will cause. It should cause basically all morphisms being isomorphisms or something like that. Yeah.
So it fails factorization.
Yeah. Yeah. Factorization is really so. You see, if the pi morphisms are trivial, then yotas can't be trivial, and the other way around. But they have to be living in the same poset, so that's what makes it complicated. Okay. Yeah, thank you for your patience, and sorry for the disruptions online.
Zurab, can I ask a question?
Yes, sure.
I was thinking about the what we don't know section. What happens if very naively you take an Noetherian form over set, for example, and you pull it back along any topological functor or monadic functor? Can you transport Noetherian forms in this way to any topological category, for example?
So thanks to Francois van Niekerk, I can answer your question because he has a theorem from which the answer follows. So if you take the category of sets and you have a Noetherian form over it, and you pull back along, you want to pull back along a topological functor.
Yes.
So it turns out that when your functor has an adjoint, when your functor has a left adjoint, the pullback, also being Noetherian, is almost equivalent to this being monadic, which excludes possibility of topological functions for this
metrics
pullback,
pieces or not in your classes. It sounds like
but
you
allowed
have
for algebraic ones, and that's how one
similar
gets at every algebraic
matrix
category
as
in Noetherian form.
generalization of like a semi-metric, right? So like, I don't know. Go
Seems
ahead.
like there is another lecture going on at the same time.
No, I mean, if I understand the part about this similarity metrics.
Okay.
Andor, I think we are hearing something from your room.
Yeah, I don't. It's my fault.
Okay, now it's gone. Thanks.
Ah, okay.
So the answer, Luca, is that we can't have this to be Noetherian because topological functors are not monadic.
I see.
But just to be clear, when can you pull back a Noetherian form? Under what conditions?
So G needs to be, if and only if G is monadic, and the composite preserves, I think, push-outs of these pi maps, which in classical algebra it's the case.
You're saying having a Noetherian form on a category is a way of doing homological algebra on that category?
Yeah. If you want to do it in a self-dual way, like you can in abelian categories, then that's the thing.
In a supervised way.
Yeah.
Homological algebra in a supervised way.
Yeah. There are many other contexts that are not. I mean, there are many other contexts indeed, right? There is Quillen exact categories, Yoneda Quillen exact categories, and many things. And actually, Kishan Dairam as a paper that we are actually writing together on how to define Quillen structures using forms. They're not Noetherian though. You can still do homological algebra, but in a different way.
You mean the structure of a Quillen model category?
No, not that one. Something else, which originally was introduced by Yoneda. It's called Quillen exact category. Luca, have I answered your question? Okay, I assume that I have. All right, then if then no, I'm chairing my own session, but if there are no more questions, then we could proceed to the next step. Thanks. Thank you everybody for joining online. I'm sorry for the electronic problems. We will fix it next time. We will use a wire instead of wireless.
Thank you, Zura.
Thank you, Zura, for your talk.
Thank you very much.
Thank you.
Zura, would you make also your slides available?
Yes, I definitely will.
Excellent. That would be excellent. Thank you very much.
Bye.
Thank you, Zurab.
Bye.
Bye.
Goodbye.
Bye.